Welcome back. And in this last section in ionic bonding, we're going to be looking at ionic equations. But before we look at ionic equations, we need to look in a little bit more detail at some general equations that you need to learn. So we're on page 9 of your notes and we're just looking at some general reactions, and you need to learn these equations. So first of all, looking at the reactions of acids. So you need to know that any metal or reactive metal plus an acid will give you a salt and hydrogen gas. So there's an example here using magnesium and hydrochloric acid. You need to know that hydroxide, an acid, gives you salt, again in this case sodium chloride, and water. Oxide plus an acid, again gives you the same salt and water. Carbonate and hydrogen carbonate do a very similar reaction with acid to make salt, water, and carbon dioxide. They just balance slightly differently. And last but not least, you need to know that ammonia, NH3, and an acid make an ammonium salt. The other reactions that you should know is that when we burn a substance in oxygen, we make the oxide. That a reactive metal with water gives you the metal hydroxide and hydrogen when it reacts directly with water. And that if we can thermically decompose a carbonate, it'll give us the oxide and carbon dioxide. And there are some examples there for you. So we're going to do the reactions on the bottom of that page. So sodium carbonate and nitric acid. So again, these are ones I need to know the formula of. Na2CO3 and nitric acid is HNO3. And they react together because that's a carbonate and an acid to make salt, which is NaNO3. That's my salt, and water, H2O, and CO2 gas. Now I need to balance it. Well, I've got 2 sodiums on this side, so I need 2 sodiums on that side, and I've got 2 NaO3s minuses there, so I need the same there. Where you've got an ion which is not split up, so one of the polyatomics that's not being split up, it's easier to keep it as an NO3 ion rather than a nitrogen and 3 oxygens, because it makes it easier to balance. So now I've got my carbons, my hydrogens, and my oxygens all balanced. The next reaction is calcium and hydrochloric acid. And again, this is going to make a salt, so that'd be CaCl2 and give off hydrogen gas. Again, I need to balance it. We've got 2 chlorides this side, so I need 2 that side. Last but not least, calcium hydroxide and sulfuric acid. So I've got calcium hydroxide, CaOH2. Notice the OH goes in brackets because I've got 2 of these polyatomic ions, plus H2SO4. Again, notice the SO4 does not go in brackets because I've only got 1 of them. This is a hydroxide and a sulfate and an acid, so I'm going to get water and I'm going to get my salt, in this case calcium sulfate. Again, notice I've kept the sulfates together as a polyatomic ion. I just need to balance it now because this will make 2 waters. So now we've had a look at full equations, we're going to move on and look at ionic equations and spectator ions. When we write an ionic equation, we're only interested in the ions which are actually taking part in the reaction. The ions which are not taking part we call spectator ions. So for example here we have the reaction of silver nitrate reacting with sodium chloride to form the white precipitate silver chloride and aqueous sodium nitrate. Now, the only ions which are actually taking part in the reaction are the silver and the chloride ions. The nitrate and the sodium ions are not changing. They're what we call spectator ions. So we're going to look at this step-by-step guide to writing ionic equations. Now, quite often once you start getting used to these, you'll be able to go straight from this full equation straight to the ionic equation and not have to do these middle steps. But for the moment, we're going to do the middle steps. So we have my overall equation. I'm going to split up any chemicals which are in solution. So iron sulfate basically means I have iron 2+ ions in solution and sulfate 2+ ions in solution. And I have 2 sodium hydroxide ions. So the 2 now goes in front because I've got 2 sodium ions in solution and 2 OH negative ions in solution. Now the iron 2 hydroxide is a solid, so that does not get split up. So it stays as Fe brackets OH2 solid. But the sodium sulfate does get split up. Notice the 2 has moved to the front. This is because I've got 2 separate sodium ions, and the sulfate ion stays as SO4 2- because it's a polyatomic ion and it's not changing. Now what I do is I go through and I cross off anything which stays the same both sides of the equation. So the sulfate ion here is not changing between this side of the arrow and this side of the arrow. In other words, as both a reactant and a product, it's identical. So it's what we call a spectator ion. It's not taking part. The same with the sodium ions. Now what I do is I rewrite my equation, but just using the ions which are taking part in the reaction. And that is the iron ions and the hydroxide ions. So that is the overall ionic equation for any soluble iron 2 compound reacting with any soluble hydroxide. So we're now on the top of page 11 and we're going to be writing out these ionic equations. So we've got sodium chloride solution, silver nitrate solution reacting to form silver chloride and sodium nitrate. So the first thing I'm going to do is I'm going to write out the full symbol equation using state symbols because that's important. So I've got sodium chloride solution and silver nitrate, AgNO3, aqueous, and that's reacting to form silver chloride, AgCl, solid because it's a precipitate and precipitates a solid, and sodium nitrate, NaNO3, aqueous. I'm going to now write out with all the ions identified. So I've got sodium, aqueous ions, and chloride, aqueous ions, and silver, positive, aqueous ions, and NO3 negative, aqueous ions. And they're reacting to form silver chloride, AgCl, solid, and because it's a solid it's not getting split up, plus Na positive, aqueous, and NO3 minus, aqueous. Now what I'm going to do is I'm going to go through and cross through the things that stay the same. Well, the sodium ions are not changing and the nitrate ions are not changing. I'm going to rewrite my equation missing off the spectator ions. So I've got chloride and silver ions, both of which are aqueous, reacting to form silver chloride solid. And that's my overall ionic equation. In my next example, I have copper sulfate, CuSO4 solution, and zinc, which is an element, metallic element, and it's a solid at room temperature and pressure. And they react to form zinc sulfate solution, so that's zinc sulfate, aqueous, and copper, which is a solid. Now, again, I'm going to identify all the ions and atoms. So I've got Cu2 plus aqueous plus SO4 2- aqueous plus zinc solid, reacting to form zinc 2 plus now because it's an aqueous ion, and SO4 2- aqueous, and copper solids. Again, I'm going to go through and cross through the things which are not changing. In this case, there's only one of them, and that is the sulfates. The copper is changing because it's changing from a 2+ aqueous ion to a solid, and the zinc is changing because it's going from zinc solid to zinc 2+ aqueous. Again, rewrite, missing out the spectator ions, and I have my reaction. You possibly will have recognized this as a displacement reaction. At A level, we would call it a redox reaction. So the next example, sulfuric acid solution, so H2SO4, aqueous, and zinc solid, reacting to form zinc sulfate, SO4, and that's a solution, and hydrogen gas. Again, I'm going to write this all out again. Notice this time the 2 comes in front of the hydrogen because I've got 2 hydrogen ions, and they are aqueous, and I've got a sulfate, SO4 2-, aqueous, and I've got my zinc solid. Going to now zinc has got a 2+ charge on it because it's an aqueous ion, and I've got SO4 2-, aqueous, and I've got hydrogen gas. Notice I'm not splitting up the gas. Again, I cross off anything which stays the same, and again in this case I've only got one thing that stays the same, and that's the sulfate ion. And so I get 2 hydrogen ions, aqueous, plus zinc solids, going to zinc 2+, aqueous, and hydrogen gas. And that's another example of a redox reaction. So the last example we're going to look at is sodium carbonate, Na2CO3, and we're told that is a solution, so aqueous, plus hydrochloric acid, HCl, which is always aqueous, going to sodium chloride, NaCl, and that's aqueous, plus carbon dioxide plus water. Carbon dioxide is a gas and water is a liquid. Again, it needs to balance, so I need a 2 in front of the sodium chloride and a 2 in front of the HCl. Again, I'm going to split it up into the separate aqueous ions. So again, I have 2 Na positive aqueous, and I have my carbonate, CO3 2- aqueous. Notice this is polyatomic, so it doesn't get split up. I've got 2 hydrogen ions and 2 chloride ions, and they're both aqueous. And they're going to react to form 2 Na positive aqueous and 2 chloride negative aqueous, plus my carbon dioxide gas, just about fit it on, and my water, which is a liquid. Again, I'm going to go through and cross off things which stay the same. And this time it's the sodium ions, which are the same, and the chloride ions, which are the same. If you find something doesn't balance, it's usually you've got this part wrong and you need to go back and rebalance things. Again, rewrite it, and we have CO3 2- aqueous plus 2 hydrogen aqueous, and they're going to CO2 gas and H2O liquids. Now the power of these ionic equations is this equation is now the equation for any carbonate reacting with any acid. So it doesn't matter what the carbonate is or what the acid is, the ionic equation will be the same. So we're going to be practicing drawing out lots of these ionic equations in class, and you're also going to do some test tube reactions to look at these ionic equations. But one couple of things you do need to learn before you do that, and that's looking at precipitation reactions. And you need to know that some ions are always going to be soluble. So nitrate ions, these are your NO3 negative. If it contains an NO3 negative ion, it will be soluble. All nitrates are soluble in water. Group 1 ions, the same, they are also all soluble in water. So anything with group 1 in it will be soluble. look for a precipitate being formed. That will be formed from oppositely charged ions reacting together to form an insoluble solid. As a general rule of thumb, if it's coloured, especially if it's brightly coloured, it'll either have a transition metal cation or an anion containing a transition metal. So for example, dichromate Cr2O72- is a bright orange solution. So that just finishes looking at the notes on ionic bonding. So you should be able to describe why ionic structures have such a high melting and boiling point. You should be able to go through their physical properties, such as their ability to conduct electricity. You should also be able to write out a full ionic equation from the balanced stoichiometric equation. In the next topic, we're going to be looking at covalent and metallic bonding. But until then, take care. Bye bye.